Okay, well, thank you very much. It's a real honor to have been asked to give the Dalgarno Memorial Lectures this year. I had tremendous respect and affection for Alex Dalgarno, who was, as Jose mentioned, my thesis advisor. So it really means a lot to me personally to have been invited. In today's talk and Friday's talk, as Hossein said, I'll try and make it more pedagogical. So I really encourage you to, interrupt and ask questions as I go along. Today, I wanted to give one example, which I hope will convince you of the close relationship between observational studies of astronomical objects and the underlying molecular physics that is so important for interpreting them. So I really have two case studies in this lecture. The first one, which I'll go through today, concerns diffuse interstellar clouds. So these are clouds of density just a few tens of particles per cubic centimeter that are found all over the galaxy, and how we can learn very interesting things about the environment in which they're found through observing hydride molecules, by which I mean molecules containing just one heavy element atom and one or more hydrogen atoms. So that'll be today. And then on Friday, I'll go back to a topic that was actually my thesis, as you mentioned with Alex, on molecular emissions from interstellar shocks. And I'll give you some background to that on Friday. So just as a matter of curiosity, by show of hands, how many of you are molecular physicists, would you say? Or, yeah. Okay, and astrophysicists? Okay, so pretty evenly divided. So I'll try and make it so that the molecular physicists don't feel like you've come the wrong year to be able to understand what I'm talking about. But please interrupt me if I sort of assume some background that isn't obvious. Like that. Okay. So let me start by just saying some introductory words about the molecular universe that we live in. And this particularly applies to the interstellar medium, the diffuse gas that pervades the galaxy in between the stars, where there's a rich chemistry that operates that we call astrochemistry. And it's sort of amazing that we get, in fact, quite complex molecules in the interstellar gas, despite the fact that it's a very simple environment and it's very low density. And so to me, it's sort of a dramatic example of how complexity emerges in the universe. You start with atoms and then you get molecules, and there's just this tendency to form more and more complicated things. So in the interstellar medium and in circumstellar regions around stars that have lost their envelopes, there are actually more than 250 interstellar molecules have been discovered over the last 80 years. And here's a list updated as of last November. Can you read this at the back? Probably not. Yeah, I could. So I don't know whether this will mess up the Zoom, but why don't I just do that anyway? Okay. Oops. So that's obviously better. I don't know if it's good enough. But anyway, those of you in the front will see that these are ordered by the number of atoms, starting from left to right. And this figure used to be readable from the back, but as I've updated it and kept it on a single slide, the font has had to get smaller and smaller. This is actually a compilation that's maintained at University of Cologne. And there's a mixture of very familiar stable molecules that you might find in your kitchen: sodium chloride, water, acetic acid, ethanol. And then there's some very exotic radicals, in fact, some of which were first detected in interstellar space before they were even synthesized in the laboratory. So they were detected as unidentified lines in the radio spectrum. And then actually the lab of Pat Thaddeus was at CFA played the leading role in identifying some of these molecules. So that's a very impressive collection of molecules. You'll notice a lot of organic molecules, particularly as you get to larger and larger molecules. But then the question is, what can we learn from them? And so my central goal is to convince you that by observing interstellar molecules and really interpreting them very carefully, you can get unique information that is of general interest to astrophysicists. So this isn't just stamp collecting, you know, we got another molecule. These molecules tell us useful things that astrophysicists are interested in. And this really was you know, the pioneering contribution of Alex Dalgarno, who recognized this fact and was deeply involved in understanding the key processes that make and destroy molecules. So the game plan that really Alex pioneered was to combine three different things. So this is really quite interdisciplinary. So you obviously need laboratory astrophysics and related theory to be able to interpret these molecules. You need spectroscopy. You need to know the collisional excitation rate coefficients for excited states of these molecules that you can see. You need to know chemical reaction rates. You need to understand photoionization and photodissociation, because there are hot stars throughout the galaxy that are producing ultraviolet radiation that can destroy molecules. So that's sort of one leg of this tripod, if you like. Then, of course, you need to observe molecules. You measure emissions, or if you have a background source of radiation, you might see the molecules in absorption against that background. And then you need to do some astrophysical modeling. You need to have physical and chemical models for the objects that you are modeling that basically take this laboratory data, incorporate it into molecules, make predictions that can be compared to observations. So that's the basic picture behind everything that I'll be discussing while I'm here this week. So any questions before I go a little further? Yeah.
Molecules were known actually to be in the interstellar space when all started.
So I don't know about started exactly. I mean, it's been a sort of steady growth where, you know, there's a curve as a function of years, more or less linear, actually. So roughly 3 molecules a year have been discovered over the last 8 years.
I know, David, that in 1969, when Charles Towns first discovered water through its maser at 22 gigahertz, it was the 6th molecule that had been detected in the ISM. And that's probably 69 when Alex was.
Okay, so there's your answer, 6. Now there's 250. Yeah. 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 So there were 3 molecules that had optical transitions that were observed in absorption in the 30s and 40s. They were CH, CH+, and CN. And actually the story behind CN was amazing, that its excitation, as determined from observations in the 40s from the ground with optical telescopes, its excitation was quite anomalous. And the question is, why did it have much higher populations in the excited J equal 1 state than in J equal 0? It was sort of a mystery. And then in 1965, the cosmic microwave background was discovered. And it was recognized actually by George Fields, who was here, that the cosmic microwave background was actually exciting the J equals 1 state. So it's sort of a great lost opportunity for molecular astrophysics. You know, maybe they could have discovered the cosmic microwave background 25 years before it was actually discovered. And actually for many years, this was the best measurement of the cosmic microwave background at the wavelength of the J equal 1 to 0 transition of cyanogen. Okay. So let me go on and talk about some recent discoveries of molecules that have been very interesting to me. And these have basically emerged thanks to the development of submillimetre astronomy over the last dozen years or so. So most of the molecules in the list that I showed you have transitions at radio wavelengths that can be observed from the ground. But there are also some molecules, and not surprisingly, it's hydrides, which have large rotational constants, where if you want to detect them, you have to go to the submillimeter, where the atmosphere is very opaque because of a particular hydride that we all rely on, water. And so it's been necessary to go preferably to space. And there was the Herschel Observatory that was operated by ESA with participation from NASA, or from airborne altitude, where we had the Sophia Observatory with a heterodyne high-resolution spectrometer called GREAT. And then if you go to a really fantastic astronomical site like the Atacama Desert, which is an elevation of 18,000 feet, you can detect some of these molecules I'm going to talk about. And there was a sort of pathfinder before ALMA called APEX. Yeah, Howard.
I think in the case that the Herschel PAX spectrometer discovered some molecules like OH+, for example, and Sophia has discovered, but it's certainly.
Yeah, it can certainly observe molecules. That's true. OH+ was actually first detected from APEX from the ground by Carl Menton and collaborators. Yeah, yeah. So this is a list of molecules that have been discovered in the last decade or so. They're all hydrides with high frequency rotational transitions. There's a mixture of molecular ions and neutral species. And one of the main ways that these molecules have been discovered is through observations of strong terahertz continuum sources. So in the galaxy, particularly in its spiral arms, there were regions where many high mass stars are forming. And these high mass stars are very, very luminous, and they heat up the surrounding dust, the small submicron particles that pervade the galaxy, and emit very strong continuum radiation, basically thermal radiation from dust in the terahertz frequency range. So one can observe those background sources. And actually in this program that we had, we observed all these sources, but we weren't actually interested in these sources except as sort of background lamps against which we could see much more diffuse gas that happens to lie along the line of sight. And this gives us a very nice way of measuring then the column density or the surface density of any molecular species lying within these diffuse clouds along the line of sight to this background star-forming region. And another nice thing is that the galaxy is differentially rotating, by which I mean that the angular velocity varies with radius, it decreases. What this means then is that unlike if it was rigidly rotating, each cloud along the line of sight will have a different Doppler shift. And so we can distinguish individual clouds along the line of sight. So here's an example of the type of spectrum that we see. On the left, a number of molecules containing sulfur are shown. And on the right, it's just a zoom in of this small region on where near the bottom of each plot. So of course, we measure frequency, but astronomers always interpret shifts between the frequency and the known rest frequency of the molecule as a Doppler shift. So that's what's plotted here in kilometers per second. And you'll see this particular source, it's called W31C, has a strong emission line in all these, or three of the four molecules. So H2S, CS, and SO, there's this strong emission line coming from that star-forming region that we aren't interested in. But then if you look very carefully, and you probably can't see this from the back, the little dips here, and here's a blow-up, you see these beautiful absorption lines, and each of these comes from a different cloud of much lower density than the background source that just happens to lie along the line of sight. So for all these clouds, we can very reliably determine the abundance of each molecule. And this table shows that in most cases, most of these hydrides that we can measure only contain a small fraction of the heavy element that accompanies hydrogen. So there are 3 hydrides of carbon in this table, 5 hydrides of oxygen. The left column shows the abundance, the number by number, relative to either atomic or molecular hydrogen. But we know what the abundances of the elements are in these clouds. And so we could divide by the abundance of elements to figure out what fraction of carbon is in CH, for example, what fraction of oxygen in these hydrides. And all these numbers, with one exception, are considerably less than unity. So these are just trace species. But what I'm going to argue is, even though they're not major constituents of these clouds, which are mainly atomic, so you mainly have carbon plus, neutral oxygen, neutral nitrogen, and so on, these trace species tell us a tremendous amount about the nature of these clouds. So any questions on this table? Yeah, Volker.
Can you actually see in the previous slide, you showed these various absorption at various velocities? Can you really, or did you pinpoint where these were relative to various spiral arms?
Yeah, so they're typically, they seem to be in spiral arms. So in a way, the way we would do this is if we can understand well enough the rotation curve, as it's called, of the galaxy, how the angular speed is varying with distance from the center of the galaxy, then we can sort of translate from a Doppler velocity to a position along the line of sight. So that's the sense in which we do it. We have no independent confirmation of where the cloud lies along the line of sight, other than inferring it from the velocity.
The question was more that they're more associated with spiral arms.
Yes, they are. Yes, so they're mainly associated with the spiral arms where the density is higher. Yeah. Yes.
The molecules without thermal dipole moments, without spectra.
No, so all of these molecules that I mentioned have dipole moments.
Right. But the question is, how many that we cannot see are they there?
Well, I mean, the only hydride that doesn't have a dipole moment is H2, and I guess H2 plus. And those, well, with H2, we can measure in another way, looking at the Lyman-Werner bands, which are dipole allowed in the ultraviolet. But you can't see very far in the disk of our galaxy in the ultraviolet until these small solid dust particles have extinguished the radiation.
Some of them not necessarily hydrides,
Yeah, so those molecules, C2 has certainly been seen. So those molecules can be detected again in the optical, right. But I'm focusing here on the hydride. So there's only two hydrides that don't have a dipole moment. Yes, Harshal.
So you make the distinction you say the average moments relative to H or H2. Why is that?
Well, it's because some of these molecules we believe form in regions where the H2 fraction is large, or some of them are associated with H2 and some of them are not. So that's sort of determined which I've done it relative to. Yeah. So any other questions? Okay. So let's see. I was gonna try to cover 3 different ways in which these kind of observations provide useful information. But I can see with the pedagogical nature, things are going quite a bit more slowly. So maybe I'll focus on 2. I mean, the other thing I'd be happy to do is, we could finish at the hour and then, people who have something else to do can leave, and then I'd be happy to talk further. Okay. So let's say I'll make something coherent in the next 30 minutes, and then maybe I'll go back, and then anybody who has to leave, obviously do so without embarrassment or at any time. And if you get bored, it's fine. Then I'll continue with some of the things I didn't have time to touch on. Okay. So I guess the 2 I'll discuss. The first one is something that some work of Alex is relevant to, is the possibility of tracing molecular hydrogen, which doesn't have a dipole moment, with another molecule, which is believed to have almost a constant abundance relative to molecular hydrogen. So that'll be the first topic. And then I'll skip the second topic and then talk about how these molecules can be used to probe some very high energy charged particles that we call cosmic rays. So we can sort of remote sense the flux of cosmic rays throughout the galaxy by looking for specific molecules. And actually, I'll sort of tell you a different story about each hydride, and it sounds a little contrived. Why should there be a different story? And the answer is basically there are very small differences in thermochemistry that greatly affect how a particular molecule will behave in the interstellar medium. So I tried to summarize the thermochemistry in this very colorful table that appeared in an annual reviews article we had with Mary von Geran. So let me just talk you through this briefly. So the leftmost column shows the element involved. And these are all in the first 2 rows of the periodic table. They're all fairly abundant astrophysically. And then the second column gives you the ionization potential for atoms of that element in electron volts. And this is critical because if the ionization potential is less than that of hydrogen, 13.6 electron volts, then that element will be exposed to ultraviolet radiation throughout, from hot stars throughout the galaxy, and will be singly ionized. On the other hand, if the element has an ionization potential greater than that of hydrogen, and the examples would be nitrogen, oxygen, fluorine, neon, and argon. For those elements, all the ultraviolet radiation capable of ionizing them, that is radiation with H nu larger than 13.6 eV, will have been absorbed by hydrogen, which is so much more abundant than any of these elements. So those elements will be neutral. So basically half the elements in this table will be singly ionized and half of them will be neutral. And then the next two columns show you whether either the atom or the singly ionized ion can react exothermically with H2. Because if it can, that'll be typically a very rapid reaction and will be very effective at producing the hydride. So that's shown by the green boxes. The red boxes are cases where the atom or the ion reacts endothermically with H2. So at low temperature, the reaction will be negligibly slow. And these numbers are just the endothermicity divided by Boltzmann's constant, so in temperature units. So basically we're saying, for example, carbon will be singly ionized. It can react with H2, but there's an activation energy barrier of 4600 Kelvin. So if I have a cold diffuse cloud and the typical temperature is less than 100 Kelvin, then that reaction rate will be completely negligible. So basically you see there's lots of different colors here, which basically means that these hydrides will behave in different ways. And so I'm just going to go to a few of these boxes and tell the story of that hydride. So I'm going to start with this green box that refers to fluorine. So it's telling us basically that fluorine can react exothermically with H2 to make a hydride, hydrogen fluoride. And in fact, fluorine is the only element in the whole periodic table that has a hydride that is more strongly bound than molecular hydrogen. As some of you probably know, the reaction of atomic fluorine with H2 is probably the most extensively studied bimolecular chemical reaction there is. Room temperature experiments suggest that there's an activation energy barrier of around 500 kelvins. So they measure the reaction rate at room temperatures, and it's going like an Arrhenius expression with a 500 Kelvin barrier. But of course, because it's exothermic, there's also the possibility that you could have tunneling, so that even if the kinetic energy were below this activation energy barrier, you still could have a significant probability of forming HF. And Alex and his collaborators basically analyzed this. Obviously, it depends quite sensitively on what you assume for the potential, and concluded that there was a substantial tunneling probability at low temperature. And this was then confirmed and determined quantitatively in the lab, where they could measure this reaction at temperatures as low as 27 Kelvin. So what this means then is that even at the temperature of one of these diffuse clouds, less than probably 80 Kelvin, fluorine can react with H2 to form HF. And then there are just two things that destroy HF. It can be photodissociated by this ultraviolet radiation I mentioned, or it can actually react with carbon plus, which is very abundant. Most of the carbon is in that form, to form the CF plus molecular ion, which is also detected in the interstellar medium. Here's some models then that Mark Wolfire and I made that show how we would predict the abundances of various species to vary as you move into a diffuse cloud where the shielding gets larger and larger. So the left-hand side is basically the surface of the cloud, and then we've computed what we expect as a function of depth in the cloud. And as you go deeper in, the UV radiation is shielded more and more, and so you start to get molecules. The first molecule you get is H2. It can shield itself from ultraviolet radiation. And then you have the various carbon plus, and then when you go in, it's neutral carbon, and eventually you get carbon monoxide. And if you look at the fluorine, though, you can see that the hydrogen fluoride, which is this curve, follows H2 very closely. So as soon as you start to get a little bit of H2, you start getting hydrogen fluoride. And what this means then is that you can detect H2 indirectly by measuring HF in regions where it's very hard to detect other molecules, in particular CO, carbon monoxide, which is the main way we look at denser molecular clouds, could actually be less abundant than hydrogen fluoride. Yeah.
I know why CF drops as you go to an ACS2, because
C plus is going down.
It's going down, but it's going into carbon.
Right.
But what causes it to rise?
It's because CF plus is being destroyed by electrons, and the electrons in this model come from the ionization of carbon. So that's the explanation for that. So there's a lot of subtle effects that come into these molecules that you have to think very hard to understand. Anyway, the Herschel Space Observatory could detect the fundamental rotational transition of hydrogen fluoride at 1232 gigahertz. We had a survey that did observe 47 diffuse clouds in the disk of the galaxy. What this figure shows you is a comparison between absorption by hydrogen fluoride and absorption by water, which we could also detect with this observatory. And amazingly, the hydrogen fluoride gives stronger absorption than water, even though fluorine as an element is something like 10,000 times less abundant than oxygen. So that's nothing to do with chemistry, that's to do with nuclear physics and how these elements are made in stars. But fluorine is way underabundant compared to the nearby elements in the periodic table. And yet, its lines, its absorption lines are as strong as those of water. And this then basically is telling us that exactly as you would expect, thanks to this quantum mechanical tunneling, hydrogen fluoride accounts for a very significant fraction of all the fluorine in the gas phase. So what's the importance of this? Well, it means that we can then detect H2 simply by looking for hydrogen fluoride, or we can, and we're not detecting H2, but we can infer how much molecular fraction there is, or how much H2 there is by measurements of hydrogen fluoride. This line of hydrogen fluoride is completely, or almost completely unaffected by absorption due to interstellar dust. So we can see it all the way across the galaxy. We want to look directly for H2. we basically have to look at ultraviolet transitions. We look at a background hot star, and then there are the Lyman and Werner bands in the UV that we can measure. But at ultraviolet wavelengths, the radiation can travel no more than about a kiloparsec, so only a tenth of the distance from us to the center of the galaxy. And so we're really can only look in the very local region. You had a question? Yes, one can. So that's certainly something that's been nicely measured, ortho and para-hydrogen. Well, the UV spectrometers have sufficient resolution that they can resolve row vibrational structure. So you're going to, it's a band, and then you'll see different vibrational bands, and then within each vibrational band, you'll see different rotational lines. So you can just measure the surface density of all the different molecules. Well, I don't know if you're going to be able to come to my talk on Friday, but I'm going to talk extensively about the ortho to para ratio. And there are some cases where it appears to be out of equilibrium, which is very interesting. It tells us that there's a time dependence. It almost serves as a clock, how long the gas has been at its current temperature. No, I don't know if what limits there are. The expectation is that it would be much, much weaker than HF. So there are some deuterated molecules, and this is another topic that Alex worked on, where the fraction of the deuterated version to the hydrogen vastly exceeds the fraction of deuterium in the universe to hydrogen. But because of this endothermic reaction, exothermic reaction, we just wouldn't expect that in the case of hydrogen fluoride. So if it just reflected the cosmic ratio of deuterium, which is 10 to the minus 5, there'd be no hope of detecting it. Okay. Well, you've had a lot of interesting questions. I'll go briefly then through the second topic, or rather the last topic, which concerns these cosmic rays that pervade our galaxy. So the background for this is probably most of you know very well. Cosmic rays were discovered a little over a century ago by Victor Hess, who you see here is going to go up in a balloon. So here he is in this wicker basket, and he went up in this balloon to an altitude of 17,000 feet. It's kind of an insane thing to do. And why did he do that? Well, he brought with him an electroscope, this device where you charge it up and there's a leaf flies up like a little flag. And then eventually, because of the ionization of the air inside the electroscope, the leaf goes down because the charge leaks away. And it was recognized that at ground level, the air was slightly ionized because electroscopes didn't keep their flag up forever. And it was believed that radioactive decay of materials in the crust were probably the source of the ionization. So the expectation is that if you went up to high altitude, the air would be less ionized, and the electroscope leaf would stay up longer. And what Hess found was the exact opposite. The ionization rate was higher at high altitude, indicating then that the source of ionization was extraterrestrial. And he received the Nobel Prize for the discovery in 1936. There was a lot of controversy about the nature of these cosmic rays, and then it was eventually agreed or proved that they were charged particles as opposed to gamma rays or some other source of ionization, which Compton had been advocating. I'm sorry, which Millikan had been advocating. Compton was saying they were charged particles. And we now know that they exist over an incredible range of energies, up to an energy of about 50 joules is the most energetic cosmic ray that has been detected. So that's the kinetic energy of a fastball thrown in Little League Baseball in a single proton. So the Lorentz factor is 10 to the 12. So these are quite remarkable. And this shows the spectrum of them over many, many orders of magnitude. But they actually account for a significant energy density compared, say, to starlight or the thermal energy of the interstellar gas or the magnetic energy of a little over 1 electron volt per cubic centimeter. So, we think of the galaxy as being filled with light, but actually energy-wise, it's more correct to say it's filled with cosmic rays. So what do these cosmic rays do? Well, they can interact with the interstellar gas. This actually leads to gamma ray production if the cosmic ray energy is sufficient, because you get a neutral pion that then decays. But at lower energies, the cosmic rays mainly have the effect of ionizing and heating the interstellar gas. And so one question is then, can we use observations of molecules to infer what the density of these low cosmic rays is elsewhere in the galaxy? So I'll move a bit faster now, but near the Earth, there's a certain ionization rate per hydrogen atom that you would infer based on the cosmic rays that you measure. And it's something like 10 to the minus 17 per second. So if you just had the cosmic rays that you can directly measure locally, they would lead you to think that elsewhere in the galaxy, the rate of ionization would be this number. In other words, a hydrogen atom would stick around for 10 to the 17 seconds before it was ionized. And one can use molecules to estimate what the ionization rate is now in molecular clouds elsewhere in the galaxy far away. So for example, observations of HCO plus can be made in dense clouds that are almost entirely molecular, and the number that one gets is in almost perfect agreement with what one would expect given the cosmic rays that you can measure at Earth. But then there was a big surprise roughly 20 years ago when Ben McCall and Oka and others were able to measure this ion, H3+. So this is a fascinating molecule, was actually discovered by J.J. Thomson, the discoverer of the electron. And Oka in Chicago elucidated the spectroscopy so that it can actually be detected in the infrared at around 3 to 4 microns. And it probes cosmic rays ionizing molecular hydrogen, because this produces first H2+ that will then react with H2 to form this H3+ ion. And you really need to understand the physics very well. In particular, you'd need to know how quickly H3+ is destroyed in dissociative recombination in reactions with electrons. And this was measured in the lab by Ben McCall. And the conclusion then, combining this laboratory measurement, this was a Nature letter, with the observations and a model, the conclusion was that the ionization rate along this sightline that he observed was something like 40 times what it is in diffuse clouds and 40 times what one would have expected. And that remains to this day a puzzle. The now observing many different sight lines where you can see H3 plus. The average value is something like 10 to the minus 16. So it's still an order of magnitude larger. So it seems then that probably what's happening is there's a certain ionization rate, a certain density of cosmic rays throughout the galaxy, and the region of the sun is atypically low. And then these cosmic rays are shielded from the interior of denser clouds that have a larger surface density than the more diffuse clouds where you can measure H3 plus. And as a result of the shielding then, it drops from this value down to a lower value that by coincidence is the cosmic ray ionization rate in the solar vicinity. So I've been trying to extend this by looking at another molecule that can probe the cosmic ray ionization. So here's H3 plus, but if you go to an even more diffuse cloud at lower density that in fact is mainly atomic, just has very few molecules, there's a couple of molecular or 3 molecular ions that you would only expect to find insofar as cosmic rays are ionizing the gas. And these ions are OH plus, ARH plus, argonium, which is a thing in astrophysics now. So it's the first molecule containing a noble gas element, basically protonated argon atoms, and also H2O plus that you get when OH plus reacts with H2 again to form H2O plus. So the bottom line is then that if we analyze observations of these 3 molecular ions that we could make with the Herschel Space Observatory and also now with SOFIA, NASA's airborne observatory, the number is in almost perfect agreement with the number that you get from measurements of H3 plus. So that suggests, at first blush at least, that there isn't much shielding as one goes from a very diffuse atomic cloud to a somewhat less diffuse molecular cloud, and that the shielding of cosmic rays only comes into play at higher densities. But this is all very reliant on fundamental processes, and there are a number of key processes that one really needs to understand to be able to really say for sure how the ionization rate measured by OH plus differs from that measured by H3 plus. One of these is the dissociative recombination of OH plus, which I gather dissociative recombination rates are virtually impossible to determine theoretically. So one has to measure them in a storage ring, and this was done for OH plus. But then there's a question of what is the rotational state of the molecule that you're actually measuring. And you really want it to be in the ground state, which is what will be the case in the astrophysical environment. And there's a new facility in Heidelberg that is for the first time capable of measuring this in the ground state. And this has been done recently by Abel Colosi and collaborators. And we're still collaborating with them to determine exactly the implications that this will have for the interstellar medium. Okay, so I guess I'll just say 2 minutes worth about the future, which is that the kinds of observations we're interested in are being pursued further beyond what could be done with Herschel, which had a finite lifetime. It's cooled cryogenically, as a big dewar of helium. Once the liquid helium is boiled off, that's the end of the mission. So one sad day, it was the temperature of all the receivers in Herschel started creeping up, and we knew the helium had been exhausted and we'd never be able to observe again with Herschel. But we do have SOFIA, this airborne observatory that also has a high resolution heterodyne spectrometer. And we submitted a legacy program that was approved for a really large chunk of time to pursue these studies of hydrides. So we got 82 hours. So SOFIA gets about 500 science hours a year. So this is a significant fraction of, not the majority, but it's a big chunk of Herschel time devoted to this subject. And we'll be observing these hydrides that are listed on this line here. And basically, we've just started to get data from that. And the first publication has just recently been posted on AstroPH that is basically just based on only about 10% of the time we hope ultimately to get. But what this will allow us to do is probe many more sightlines throughout the galaxy than had been done with Herschel. So this is the location of the center of the galaxy. This is the sun. And then all these dots are the 25 different sources that we'll be observing. So we should really be able to understand, for example, the cosmic ray ionization rate and how it varies in the galaxy much better than we do today through observations of these molecular ions. Okay, well, sorry that was a little rushed. I think it was good though to have the to and fro, and why don't we break here now and I can talk a little bit more about this for anybody who wants to stick around.
Be voting that once it's no. Well, I mean, I can send you the thing. Yeah. It's just share. Yeah, it would be recorded.
Yeah, hi.
I wonder, those H2 plus helium, cross-section reaction with helium plus.
Right. So in the colloquium on, so we have discovered helium hydride plus, but it wasn't in these diffuse clouds. And it isn't produced effectively in these diffuse clouds. That reaction you mentioned is slightly endothermic, or it's only rapid for H2 plus in V equal 1. So we don't expect, nor do we see helium hydride in diffuse clouds. We actually see helium hydride in a much more weirder environment, actually, where a young star is heating, and it's not a young star. It's a star that has evolved off the main sequence, so and has lost its envelope. So it's a white dwarf. So it's a very hot star. It's a young white dwarf. It's very hot, and it's ionizing the shell of material that the star has recently lost, and it's hot enough to produce quite a lot of helium plus. And helium plus, and this is another thing that Alex and collaborators calculated, can undergo radiative association with hydrogen atoms, of which there are some also. So you get this thin shell of HEH plus, and that'll be the subject of my colloquium on Thursday. Yeah.
Just a side note, we showed that beautiful spectrum of cosmic rays, flux versus energy.
Yeah.
And it just recalled that, there were groups that tried to stop the turn on of the Large Hadron Collider for fear that it would create black holes. consuming the earth. And the counter argument
Was-
was basically, the earth is bombarded with particles of energy significantly higher
Right,
than the LHC. And we're still
Right.
here. So,
right. So the LHC is, I guess, rest mass. It's 11 teravolts, I think.
something.
So that's sort of up here.
Yeah, yeah. I mean,
Yeah.
this is,
Yeah, right. Yeah. 9 TeV. Yes. 9 plus 9. Yeah, yeah, right. The current one is 6.5 plus 6.5. Yeah, yeah. So we have to worry, we have to wait a long time till we start probing unknown areas of parameter space. Yeah. Oh, that it would result in some catastrophe. Oh. Okay.
David.
Yep.
David is in room C311. Meet him. And,
Yep.
very nice.